Yeah, so last time we looked on the description of the random feature model where we have a non-linearity, and in principle we understood this by looking on the cumulants of the entries of this matrix, and we saw that this feature matrix, which is given by taking a nonlinear function of the entries of a matrix, which is given by the product of two Gaussian matrices, that those cumulants have a specific structure, at least in the asymptotic regime, so in leading order. And this was that they must have a cyclic structure in the indices, and then we could describe what they are. So here maybe I just recall, so the entries of my matrix I denoted by Fij, and we had that essentially there are only cyclic structures there. So this means we only have a second order cumulant, and then the cyclicity just means that this must be the same entries, and this was given by a theta 1 of omega. We had for our nonlinearity omega, we calculated two numbers, theta 1 and theta 2, and theta 1 shows up here. Okay, and all the other cumulants which make a contribution, so those are cumulants of even length, but bigger than 2, so r is here bigger than 1. So that we have here the 4th, the 6th, and the 8th cumulant, and then we must have here a cyclic structure, which means that I have here I1, J1, and then I have here I2, but this J1 must repeat here, and then in the next entry this I2 must repeat here, and I continue here with a J2 up to the end where I have an F I1 JR. So I mean I have always two I's, no, I have two J's repeating, and I also have two I's repeating. Only the last I repeats at the last position. Okay, so maybe last time I had this wrong, but anyhow. Okay, so that's the cumulants which survive, and all of them make the same distribution. So namely, it is 1 divided by p. P was the size of our datas to the r minus 1. So this is the r here. And then we have here a theta 2 of omega. Okay, so if r is equal to 1, I mean this guy here is essentially the same as here, it's 1, but here we get a contribution theta 2, not a theta 1. Yeah, okay, that was the leading order, and of course there are subleading orders, but if we calculate the eigenvalue distribution in a limit, then only those guys make a contribution. And of course, the bigger r here is, the smaller the contribution is. So p will go to infinity. So this means the higher order cumulants are smaller, but there are more of them. I mean, I have this here for all the I and j's showing up here. And if I calculate moments of my matrices, I take traces and I sum over all those guys. So each of them is smaller, but in the sum, they are of the same order as this guy. Okay. And this also means that here I assumed, or I wrote down this formula only in the case where all the i's and the j's are different. Because otherwise, I have a cycle structure. If they are all different, I only have one maximal cycle structure, which I can control very well. If some of them are the same, there are sub-cycle structures which would also make a contribution, and it's hard to control this. But okay, I don't need the other ones, because if some of them are the same, there are less there available. Okay, so in my calculation for the eigenvalue distribution, the ones where some of the indices are the same don't contribute. So it's good enough to know those. Okay, that's good, because I mean, if here are some are the same, it's hard to control this. So I cannot write down a formula for this. So I don't bother to think about this, because we don't need it. Good. Okay, and so from this, then we saw, or at least I indicated, how you can use this for deriving an equation for the Stieltjes transform, and this in the end leads to the Stieltjes transform which I had in my theorem for this situation. Okay, and this is in principle, yeah, not easy. I mean, I didn't really show you all the steps because I mean they are all elementary. They can be done, but you have to look on many cases. You have to see which terms asymptotically vanish and so. So it's a quite technical and tedious work, but in the end you get it. But maybe the one point which I want to make at the end is that this cycle structure, what you observe here, which in the end gives you the result, this also shows that nonlinear model, which we are looking at, is actually equivalent in the sense that it has the same eigenvalue distribution to a linear model where we are adding noise. That's what we observed in the beginning, but what we also observed in assignments. So let me just talk a little bit about this. Okay, so I mean, what we are looking at, this feature matrix, so this is given by taking this Wx, and we normalize this by square root of p, but then we also apply a nonlinearity sigma to this. Okay, I mean Wx, this is relatively easy to control. The application of this, we saw that it has the effect that the cyclic structure of the cumulants is preserved, but the actual value is replaced by theta 1 and theta 2, but we got this. Okay, but now the point is that this here has asymptotically the same eigenvalue distribution if I take this guy here without a nonlinearity, but then I'm adding a noise. So the effect of applying these nonlinear mappings to the entries of my matrix is in the asymptotic the same as adding a noise, another Gaussian one. So maybe I compare this to F twiddle, which is a linear combination of this guy here without the sigma, and this linear combination of course contains this theta 1 and theta 2. So I take square root of theta 2 Wx divided by square root of p plus, and then I have theta 1 minus theta 2, and we know that theta 1 is always bigger than theta 2, so this is okay. And here I'm adding z, where z is another Gaussian matrix which is independent from w and x. Okay, and so in principle, to see that the eigenvalue distribution of f transpose and the one of f twiddle transpose is asymptotically the same, it's enough to see that in leading order the cumulants are the same, because they determine everything. From the knowledge of the cumulants, we were able to calculate, to derive the equation for the Stieltjes transform. So if I denote this here by Fij twiddle, so we should see that I have fabricated here a random matrix model where the entries have in leading order the same cumulants as the guys of this. Okay, and this is quite easy to see because we know that how cumulants behave with respect to independence. Okay, so namely let us look at this. So let me first look on the higher order, so the K2R. Now I take the ones of the F twiddles, so Fi1 J1 twiddle up to Fi1 twiddle JR. Yeah, so what is this? This is now, so each of those guys is now a linear combination of an entry from here plus an entry from here. So each of the entries here is a sum of something coming from here and something coming from here. And then the cumulants are multilinear, so I can multiply it out. So I will get terms where I only have here terms coming from here. I will have terms only coming from here, and then I will have many mixed terms. Okay, but the entries here and the entries here are independent, and we know that for independent random variables, mixed cumulants vanish. So all those mixed terms are 0, and I only remain with the guys from here and the guys from here. But of course, this guy here is a Gauss matrix, which means the entries are Gaussian variables, and this means only second-order cumulants are there. Okay, so this means because here I'm in the regime where r is bigger than 1, I have here a fourth or sixth cumulant, and all those guys here don't have cumulants of those order. Okay, so this doesn't show up here. So the only contribution which I get here is really the one coming from here. Okay, and this Wx, I know they have the same cyclic structure of the cumulants. So it's only the cumulants, the cyclic ones, which make a contribution. And so, and those are the ones which I consider here. And so what do I get? Of course, I mean, each of them has this factor square root of theta 2. And I have these 2r times. So I get here theta 2 to the r. Yeah, I have 2r times the square root of theta 2. So I have this to the 2r. And then I'm left with the cumulants of the entry of this guy. And that was what I denoted by G, the Gij. So I have here the entries of the G's with the same cycle structure here. So Gi1, J1, up to Ji1, IR. Yeah, but those are the cyclic cumulants of this product of the two Gaussians, and that was what we also observed before, that they make exactly the contribution 1 over p to the r minus 1. So this is 1 over p to the r minus 1. Huh? Yeah. Okay, because this was the situation where I don't have the nonlinearity, where we had the same structure here, but the theta 1 and the theta 2 were just not there. Good. Okay. Oh, yeah, they were just 1. Okay, so you see for the cumulants of order 4, 6, and so on, we get exactly what we need, because I have here theta 2 to the r. Okay, so I was missing the to the r over there. I get here is to the r. That was what we calculated last time. And here I get the same. Okay, and now it's only the second order cumulant. I mean, if the second order cumulant would also just be theta 2, then of course I wouldn't need this term. But the second order cumulant is a theta 1. So I must somehow repair. I must make out of a theta 2 a theta 1. And of course this is exactly done by adding this thing here. Because so how's the situation for the second order cumulant? So there I have kappa 2 of Fij twiddle, Fij twiddle. Okay, and now again, this is a sum of entries from here plus entries from here. So I multiply it out, but mixed terms vanish because of the independence as before. So I only get a contribution where I have only entries from here or only entries from here. But now I have a second order cumulant, and now this makes a contribution, because the second cumulants of a Gauss, they are 1 in this normalization. So what I get here is now I get the theta 2, because I have twice the square root of theta 2, the cumulant of the entries from this matrix, which I denote by Gij. And then I get this to the square. So I get theta 2 minus theta 1 times the second order cumulant of the entries of this matrix set. Let me denote the entries by set ij. And those are just standard Gaussian variables. So this means their cumulant is equal to 1. And those guys here, they have, again, also the cumulants equal to 1. Because those are the cumulants of this, and they are also equal to 1. I mean, the cumulants of this guy are the same as if theta 1 would be equal to 1 and theta 2 would be equal to 1. Yeah, okay, but now you see that now I have here theta 2, and here I have theta, no, I have here what? Theta 2, yeah, here I have theta 1 minus theta 2. Theta 1 minus theta 2. So I have theta 2 plus theta 1 minus theta 2. The theta 2 cancels, and I'm just left with the theta 1. So the whole thing is just theta 1. And that's what it should be. So with this simple linear combination, I have fabricated now a random matrix which has in leading order the same cumulants. Of course, the subleading orders of this model are different from the subleading order of the other model, but for in a limit, this doesn't make a difference. Good, okay, so you see that, yeah, we can somehow understand this maybe quite strange phenomenon that applying non-linearity, I mean in this model, this is a very specific model, but at least in this model, applying the non-linearity to the entries of our random matrix has essentially the effect that we forget about the non-linearity, but that we are adding a noise, an independent noise. Good, okay, so maybe that's about the concrete calculation for this. Yeah, and so what we observed here is replacing a nonlinearity by addition of a noise, so replacing a nonlinear model by another linear model is actually something which probably is true more general, and I think there is quite some activity at trying to prove this in general situations. So I mean, this is usually very often this goes under the name of Gaussian equivalence principle, that essentially if you have a random matrix which might be quite non-linear, you are replacing it by another linear one which has somehow the same leading features, or cumulants are the same. Okay, but of course you have to prove that the questions you're interested in really are the same for both of them. And at least in this concrete model we saw this more or less. In other situations maybe it's not so clear, but there are at least conjectures and work going on in this direction.